my generator's down. My carburizer's not running. So this is a no-brainer. However, how do we get this? The core and the heart of IIoT is data center. Okay, here's a representation of all of data. Could be on-prem, not, we'll get into that later. However, you are now introduced to this information, but how do you get this, right? How do you do that? And the thing is, the truth is, it's not fully known. When you start off, you don't know, because I don't even have that generator yet, because I'm in whatever, nitriding from Nitrex. I always think nitriding first. But one of the first two things that you will implement is, if that generator is okay, then that carburetor is working. And this is going to be pre-programmed because NFPA forced you to, and because common sense tells you to. So this has been done. But all of this other information, if I have access to it, then I can link it, all right? But I need to have an easy way to tie the variables. I need to have an easy way to visualize the data that I have, right? So I have a garage door app on my phone, and I have an alarm system app on my phone. So if my house is armed, wouldn't it make sense that if accidentally I press the open garage door, it should not open because it's armed? I should be at the keypad of the control panel of the alarm, or disarm first, then open the garage door. But if the systems are completely independent, you can't get that. But linking them is the key, right? So the information is there. So we take our information and we kind of categorize it. Now, this data center is, I can't underestimate how important it is. ERPs, SCADAs have a database, and yes, I'm logging, and a lot of this information is available. However, this SCADA, those furnaces in this database, ERP in that database, in Excel is another key source of information. But if I am able to capture this data and lock it and categorize it, and I now am able to pull it out anytime I want, I now have formed the foundation for machine learning and digital twin. Recognize correlations. So having this data center, I now run some sort of a machine learning algorithm to look at my data and see, of all the data you found, what influences my decision, okay? I'll come back to this in a second, but basically, let's say, what information in my data center will affect K-step? What information in this data center is needed to start a furnace? So this, what I did here is a representation of the heat map. So the information right here is very influential to that decision, whereas this information, not so much, right? We'll come back to the details in a few minutes. So now, let's just brainstorm. I'm trying to predict K-step, right? And out of the top of our head, we know time, temperature, potential, we take it for granted. What about alloying elements? If my furnace heats up faster, will it affect K-step? The RPM of the fan, does it affect K-step? Is the surface, quench time, endo flow, does it affect K-step? So I'm not sure, but I know all this information. And I want to predict which of these are going to affect, in this case, K-step. I want to create a predictive model to analyze this and let me know what is heavy, what is important, right? Running it, we're going to generate rules that come up with this heat map. We're going to be able to take those rules, analyze them again, put them back in our original data, and see how that K-step predicts. And we're fine-tuning this K-step by seeing that, yes, time, temperature, potential are heavy influence, but RPM of the fan is not. We could see that quench time didn't have an effect on K-step, but stability of the atmosphere did not. So it will that's what I meant with that heat map representation, where this information is highly influences the desired outcome versus others are not. Right, so now running supervised learning will show correlations that may not seem apparent at first. We can now take these rules and run them again, through the model to come up with a better prediction. If I have the data in my data center and I run certain statistical analysis on it, okay, so I'm going to run a Pearson. This is basic. So a Pearson or a Spearman algorithm to see what is heavy influence between one and another parameter. I can generate a graph like this. This graph here represents things like carbon content, magnesium, diffusion speed, maximum dissociation. This is an example in night writing, to maximum temperature or whatever. These variables are also here. So maximum temperature has a certain coefficient compared to, I don't know, stage time versus temperature and this and that. What's important here is using, first you run it Pearson, then you run Spearman. What's important here is you'll see things that are either heavy, neutral, or heavy but on the opposite. So for example, I apply power and I increase temperature, or I don't know, in cooling I apply power to drop temperature, right? So I'm interested in what is very green or very red. And those are the factors that either linearly or non-linearly has determined that, well, this and this have a negative 0.7, whereas this and this has a 0. So once you do this, now you eliminate things that are not so important, that you don't want to overload your CPU power on calculating things that are not important. So in this case, I would see, in that original example, the garage door would not affect my K-step. But to get this, especially with like the benefit of Nitrex, I had years of log files from night riding furnaces. So we took these years of log files from the original DOS era days to recent log files in my many furnaces that I have the luxury of having, and compile all this and have machine learning analyze all these things. I also have a lot of metallurgical reports that we've done over the years. So we correlated these results, this material, that job number, and we built up our data center. So this was applied. Now, one of the things about sensors, some furnaces have sensors on temperature and power, it's guaranteed every furnace would have. Other sensors I may not have. I'll give you an example of how I could derive a sensor from other sensors. So in a vacuum, I have 12 thermocouples. That's 12 TCs. In Excel, I have 12 lines. Temperature, time, going on forever. There's always new data, 12 of them. Now, one important variable in a vacuum is what's the coldest temperature and what is the hottest temperature of the enabled TCs. Let's assume all 12 are enabled. In Excel, the 13th column would be min temperature, and the 14th column would be max temperature. Maybe the 16th column would be average temperature. And now, in the cloud, I create these new sensors as they're running. No one is looking at them yet, but I do that anyway because that's a variable that I think I'll need. And I don't want to calculate it when I do an analysis of the last 5 years. I need to calculate that value over that'll take forever. So CPU power is going nuts. So this is why a lot of variables I would like to create. Here's an example of a furnace with, let's assume I have an energy meter. So the energy meter could be put on zone 1, zone 2, zone 3 power, or like a cubic foot of natural gas for power, for heating and that type of thing. But I have it on the furnace, or sorry, start from the zone to the furnace to the plant. So I can only read what's happening on the plant level. How am I going to find out what's happening on the zone, right? The thing is that that's one data point is kilowatts now, current. Okay, so this is equivalent to my odometer. I'm at 100,000 miles at noon. But at 1, I'm at 100,000 miles and 60. And I record that. Well, I was doing, on average, 60 miles an hour. So with my odometer, I was able to calculate my speed. So what I'm doing here is, regardless if it's in the zone or not, I have, let's say, the red would be my miles or kilowatts of the total plant or total furnace. And then I could see when we went to heating, the slope went up, right? So this allows me to calculate or visualize that now my amperage is going up. So maybe I don't know the actual power, but I could derive it. So this information, when we have it, we're going to want to store that as a data series as well, because it will be imported later. So let's move it to machine learning. So I had my log files, which has all the information that I had recorded back then. I have quality, which I hopefully measured everything I measured, and hopefully I recorded things like the alloy and any surface condition, because I may not have back 15 years ago. So I put all of these together and I get supervised learning to analyze and look at the log files, look at the results, and come up with an algorithm, which if you were part of the previous conversation or discussion, it's exactly that. You want to find out what is the result I link, and it's going to find the model, which is the software. So supervised learning takes that information, applies a certain formula, and comes up with a model. Now, again, the model could technically be this super duper complicated formula. And we want to simplify it. But at this point, we still need good CPU power, which this guy does not have. And we want to create our models that are going to be efficient to us. So that super complicated algorithm is not easy for us to work with. So let's try to make them linear. If we take typical k-step formula, it's this. This could turn into k. So k-step is the depth times k times root time. Okay? And root time is the square root of time. Square root of time is not just multiplication, it's now square root. So let's say we want to simplify square root so that something less powerful could deal with it. Then at that moment, I may decide that I'm going to, when I record my temperatures and my power and whatever I'm recording at this time, I also record what's the root time, and I record it. So now I have a new variable called root time. So this root time gives me something I don't need to calculate later. Now, if I apply the model on the simplified variables, so I try to take everything linearly, I can apply different complexities. So here I'm telling my software to go with, just y equals x, k-step equals 5. Okay, I'm accurate, but I have a huge standard deviation, it doesn't work. The k-step is equal to y equals, or k-step equals mx plus b, right? The equation of a line. So now it's linear, one exponent. It's not very accurate. So I can increase my complexity and getting my formula more and more and more complicated, okay? And now this is what we want to avoid, having all the CPU power forcing and calculating lots of data. So we take this and just throwing it into our prediction. Here's an example. I want to read furnace pressure, and I'm going to show you green here is furnace pressure, and predicted is dotted red. According to exhaust valve reading, furnace atmosphere ammonia, total flow, and thermocouple interior 1. The model, according to like level, I don't know, 4 complexity, calculated those guys here are most involved in pressure. And this is something that humans won't appreciate in the big picture because we don't see the link of RPM, for example, and K-steps because it doesn't make sense. AI may see a link between them, and that's the beauty of it. But again, we take this complicated equation, and we're going to make a linear feature. So now, we try to go to something that is easy for low CPU power to calculate, to handle. So we're trying to get to this red line here. That's our goal, which is K-step versus whatever, different times, let's say. And according to K-step is equal to some value plus this is one of those previous numbers, 0.7, 0.2, 0.5, negative 0.7, all those numbers, times root time. Like that was just an example. Obviously, this is not a finished sentence, right? Equation. But I throw in temperature in there and time and potential, endo flow, status of the loading dock, which will probably have a 0.000001 times loading dock, yes or no. Okay? And you get to these blue dots. And you can now play with your coefficients. You play with the weight. You can remove certain variables to come up with minimizing the error between your dots and that red line. So here's your theoretical K-step, and these are all the K-steps you calculated. And by playing with your equation, your model, fine-tuning your model, running it again, seeing if I use this model in last year's data, it would have calculated this K-step, but this is what I measured. So I can minimize the span and better my model. Now we're going to use the model and we're going to make it more stable. Let's recap what we saw so far. At first, I had a whole bunch of data, which included my loading dock, right? I identified what I had, and I'm going to now try to integrate it into my system. I will have some documentation, which I didn't mention, but a cert of TUS, a cert of a thermocouple, a mass flow controller, that type of thing, which is needed. I throw that in there, okay? Mostly it exists, it expires in a year, for example. I'm going to throw all this information in something we call a data lake, which is more or less the raw data, what you would expect in your Excel database, okay? And we have a data warehouse, which now I have all of these extra sensors. I have the relationship between this and that, and this was all calculated. I didn't really work too hard to get that. And now I'm going to have some sort of an API that takes this information and feeds it to this guy, let's say, okay? Now that we have that well-designed ecosystem, we're going to train on our model to its final state. Now the question is where? The server is needed. The server is needed at the beginning is guaranteed because there's a lot of data to crunch. We're going to simplify our model so that there's less data. And in the world of Amazon, Microsoft, CPU power equals money. So you want to simplify it because it costs you less to run. You are going to try to limit time so that you have your data when you want it. Again, if you don't do your homework well, when you want to open up your graph and it needs to calculate root time every single time and all the other things we didn't talk about, it's calculating on all of that information for every dot that's for the last 10 years. It'll take forever to load. So in an IIoT, we have the beauty of hyperscaling, which means imagine in your own house, you're running a PC and you're playing a game, but the game is starting to lag. Well, you just turn on another PC and now the CPU is shared to both and your game is running faster. But now your friends come over and you're playing another game and it's getting more and more powerful and you just turn on another computer. But then two friends go home, you turn off the computer. So computers can be booted and take over and help their peers as needed. So that's a nice thing about IIoT. So if I do need some crunching, it'll do the crunching and then back off. So you pay for a high amount for 1 hour, and then the rest of the 24 or 23 hours, you're not. So that's nice. I now can also have my holistic view, and on IIoT, I can have a dashboard which takes a look at the database, i.e. what's the furnace temperature, we take that for granted, but also what's the status of the lab and what's the status of like loading dock door, right? So I could see all that because it's all linked. In IIoT, I have as much hard drive space as I need. I mean, I run out, it just expands. And of course you pay for it, but it expands. Whereas if you're on your own infrastructure or in a controller, forget it. You don't have that much space and it's limited. Stability, IIoT, the beauty of it is something goes wrong, I kill that computer, I power up the other one with the previous version and it just continues running, and your HTML browser is just gonna not see it. You're running yesterday's version. Meanwhile, the bug is, obviously we're dealing with whatever the issue was, but everything can be launched immediately. Like it's very quick, and services are like, it's all, there's no hardware that is slow. Everything is fast. Let's go to our model. Now, here is, again, this one is heavy on Nitrex, but we take the model of K-stepped in nitriding, and depending on, at the same temperature, as you can see here, at the same temperature, I have here a long recipe which ended at 31 hours, and another one, no, my calculated end time should have been like 20 whatever hours, right? So I have 3.5 hours that the human said, well, we run this at so many hours and that's what we do. But according to the calculation, I could be less. Now, that is, the same model would give me here a K-step of whatever, 0.79 millimeters, which I did not convert to tau, sorry. But still, the idea is there is a real log file at one point in Nitrex history, and there is a calculated end. So I could analyze what I have done and learn from it. So maybe I shouldn't have gone so far. What I wanted to mention here is, imagine a hybrid model. So we do have human putting in a recipe, 31 hours as normal, but then my HMI telling me you achieved it. You're surpassing it. You're here. Your K-step is in real life, mathematically, of course. Then the human may decide, okay, I'm done, and stop. And if you gain confidence with this, it makes sense. All right, anomaly detection. Okay, anomaly detection is nice. Okay, now we have our well-designed ecosystem. We have all of this data. The AI is always looking in the background for every control loop. Temperature, power. Set point to a valve, mass flow controller, there's an act value to the mass flow controller, right? There's a closed loop. Every time there's a closed loop, there is an expectation that the process value is going to match the set point. So this guy is usually figuring out, okay, what's happening right now, and my set point is supposed to be 600, and I'm actually at 596.7, so he's happy. The alarm tolerance is 10, so there's no alarm, everything is great. But how does this current data compare with the past? So this little controller, he's doing his job and everything is great. However, what if that little controller knew that for the past so many years, we've always been running around 480 and 520, and that's us today. Now all of a sudden, this 596.7 makes sense. Why did the controller try to get the 600 to maintain something? Because it did. And us humans would look by the furnace and see that set point, process value, check, and continue. Because we don't have the concept of the past. Obviously, a good operator maybe noticed it, but sometimes you don't. So AI is looking at the past we have machine learning saying, well, you used to be around here, and all of a sudden you're way out there. That is an anomaly. And it's always looking at this. Old history is always looked at in the background, in the CPU power in the cloud, right? And it's always looking at, okay, this is my average. And the average is always, let's call it the error between my set point and my act value, between the k-step and all of these other things, right? This calculated k-step. So all of these things, always, the error is supposed to be 0. And on this date, it was here, it was below. On this date, it was above, whatever. Now, if I'm within a certain sigma, good, it says nothing. But if I'm outside anomalies, then I can get alerted and say, hey, we got an issue. But it's also looking at trends, right? So if here, my data is mostly going away from 0, both in the, whatever, it could be in the positive or it could be in the negative, then that's a trend saying you're not out of band yet, but you seem to be going that way. A drift is when, well, we just kind of jumped. All of a sudden something went low, all of a sudden something went high. Statistically, it's a drift. And an outlier is way like one dude completely out there, and it's, why is that? So the anomalies are always being investigated as you're running, and your history helps you predict the future. If we go to take this information and example, this is complete, let's say, good, right? 1,000, 1,002, everything is great. But here, in the last heat up times, my average for the past history used to be, whatever, 87 minutes, and now I'm at 98 minutes. It will detect it, human may not. Flow to maintain something used to be around 45 CFH, but now we're at 65 CFH on average. Machine learning will detect that, you won't. When am I in the soak stage, the power to maintain has been rising steadily over the past, whatever, 2% over the last 5 runs. It'll notice it. Okay, digital twin. So you have a real equipment and you have your model. So now you have all of this AI working in the back, machine learning, and all these equations and all of these extra sensors that are being written. And I am now going to be able to play with this guy, i.e., what if scenarios here that I know, trust will affect reality, all right? So I could play with my anomaly detection. I create virtual processes, virtual prototyping. I'm able to do all of these changes, right? I'm able to do all of these verifications. So now, let's get to our application. I'm able to consider that my twin has access to all this information. I have a comparison between live and electrical. I'm able to do a reverse failure mode effect analysis. So I can have my maintenance team punch in to fix this problem. We change the filter. When we change the filter, everything went well. It learns that changing the filter has this effect. If I'm able to know the source of the problem, I could give advice to what the solution may be. I have now the experimentation adaptation. I'm able to brute force, i.e. I really just type in change now millivolt to this carbon potential every millivolt and see what my result is going to be, brute force. I'm able to just optimize. So you learned what you learned, so now tell me what the millivolt should be to get this k-step. And then I can create my recipes. Okay, example. This is real life example. So a customer had a certain k-step that was requirement, right? 120 to 160 Ks. And they were doing this. Statistically, they were doing this bottom line here because they did not want to have any rejection. So their goal was 3.7, I think. My goal was 3.8, sorry, to not go out of tolerance, which is this red and blue line here. But if we could increase the accuracy, if I could get my system to be more repeatable and more accurate, now instead of going to 3.8, I could go to 3.3, knowing that I will not hit my bottom end, and I have reduced 26%. This is a deep case, but if I go with a shallower case, fine, I still have 20% savings. So these are real life examples. Conclusion. The concept of connecting a controller with IIoT is reality. It's at our doorstep, and data is king. We're basically going to have to allow our electronics to have more control, because the humans are not staying in this field as long, and the humans need to have insight that they don't have the gut feeling anymore. We have to have data, and we all have the data. Linking the data is the only key, and linking the data in cloud environment is actually quite easy. We design a data center, which is just your database, and having the kid program your MySQL or MS SQL is not going to cut it, because he'll be over and over updating it, so that we have future-proof access. We have to create supervised learning that is going to give us all the features that we want. We take our machine learning algorithms, both linear and not linear, we run them through. This is the learning side, offline, of course. We try to get all the information we can. We find all these features, we model the relationships. It's a very good idea to substitute and make it as simple as possible, so mathematically we have less work to do later. Keep our CPU power, i.e. cost, low. We train our model with these linearized features, and we play with our digital twins and see our new models, our new recipes, our new what-if scenarios. Thank you. Any questions?
So looking at this data, you're one example of, you were looking at temperature recovery time. You know, it took 85 minutes, the next time it took 96 minutes. So you want to, you make a change. Let's say you have the burners tuned. So how do you implement that into the learning algorithm? Is that, you know, you put a manual entry that we tune the burners, or is the system, would it be looking at like gas flow, airflow, XSO2?
Okay, well, like see, that's the thing. If you have sensors, that's great. I don't have sensors, right?
Yeah.
I don't have sensors. So now,
how does the system know that we've made this change and take that into account?
Okay. One of the easy things. So in my quick example, because I started realizing I'm running out of time. I change a filter, and my flow rate is now good. I enter it into the system so that it knows that this cause was corrected by this action. Now, if I do this enough times, that means the human had to enter. At this particular time, this was done, and the machine learning has now kind of not reset itself. So now what's able to happen is the next time that the flow is not getting to temperature, the burner is taking longer, something like that, I can get a report, a suggestion that there's a 62% chance that the filter is blocked, a 22% chance that the regulator is off, or other. Okay, because it doesn't know, because it was entered only 6 times in the last 2 years, or whatever, something like that. So it is something that can grow with time. What the blind graph will tell you is that you were running with this amount of BTU, or like amount of energy, right? Somehow electrical or gas, and then all of a sudden, poof, it dropped. And I don't have this example here. I have it on my, I mean, at the booth. You can come join me. If you're looking at a long term, you do see this information. And now, if it does not know, it'll alert you that something happened. So then, at least you're not blinded to it. So yeah, it's taking longer. And maybe it's really because this furnace has always been running springs, and now all of a sudden I put this, 5-ton piece. So that's how the system will kind of alert you. And if you know you put your 5-ton piece and it took longer, you'll just ignore. But if you're putting 5-ton pieces and 1-ton, 5-ton, 5-1, 5-1, 5-1, then your span gets wider over time. So then it wouldn't freak out, right, as much.